contributors into our budget table, and we we look at these, and some of them have more dominance than others. So we kind of really need to really ascertain exactly is it what that impact is going to be. And like I said, the two major contributors to any RF and microwave uncertainty is going to be your mismatch, and it is going to be your cable and readability. So extremely important to be able to look at those factors and to be able to identify them and quantify them. And so if we look back, typically five generic steps that we utilize when we're doing this stages of uncertainty and uncertainty analysis. The question that we've got to ask is, why do we do this? And reasons for that is it's practical. We want to understand that we're making a good measurement. We want to understand what our uncertainty in the contributors to that is. Secondly, it is the laboratory quality system operates, and as a 17025 accredited laboratory or non, you have to have a good quality system to be able to know that your measurements are good. Thirdly, we can say that so 17025. It's the accreditation that we all follow, that everybody strives for, and it pretty well tells us what we need to do, and that we need to do an estimate of the uncertainty of the measurements, and we have to report those. So, and this applies to every type of laboratory, whether you're a calibration laboratory, whether you're a testing laboratory, and so on. So, and there's the five major generic things that we need to identify when we're doing that. That's going to be identify all the sources of error. We're going to separate those sources of errors into a type A and type B. We're going to apply correction, if possible, anywhere on the B, because if we can apply correction, that makes our measurement a lot more straightforward. And then we're going to calculate. We're going to calculate and combine those uncertainties and together. So we. Hello. I heard somebody say something. Apologies.
Excuse me, Bill. We have some reporting that we have some audio difficult. If there's people out there some difficulty hearing this, could you please send the chat and we'll see if we can.
Let's see. The audio problem that I had is when you were speaking earlier. But we did a test. I was pretty good. Can you guys not hear me clearly? Still?
So we've got we've got a couple people having some difficulty.
They basically just said that it was your audio that was not clear. Okay.
Go ahead, Bill. Sorry, folks.
No problem. As a matter of fact, I can hear you a lot better now. All right. So then once we combine all these uncertainties together, we got to come up with the calculated expanded uncertainty. And typically, what we reporting in calibrations is a k equals 2. And then we're going to get into a little bit more of that. We're going to look at it being a 95% confidence level, and because this is what we report in calibration certificates, and it's pretty well mandated by the 17025. So it's a good way to kind of look at that and move on. So on occasions, and we'll get into this a little bit, we also have a 99%. Which we'll talk about that a little bit later. But the average, the common reporting k equals 2. So we go with that pretty well, and as a standard. So and two types of uncertainty. There's a type A and a type B. You know, at one time, type A was what we knew was as the random uncertainty, and type B was the systematic uncertainty. That terminology has changed a bit, you know. So, but type A is measurements that we can statistically evaluate and take the data. You know, where we can look at it. And they're repeatable, things that influence the measurement, like jitter, noise, signal stability, and type of measurement. Now, uncertainties are uncertainties that we that cannot be statistically determined. However, there's other ways to really look at it and and judge them. So, you know, we will make judgments based on the data that we have. You know, a lot of times you may have a lot of detail of the uncertainty, and sometimes you won't. So, you know, we've got to do that. There's other occasions where, you know, the uncertainty, the equipment specification, you know, they just give us a value, and that's the value that we've got to go with. You know, there's others like the instrument resolution, you know, a critical factor on where we've got to go, you know, so we want to be able to identify that. So we look at mismatch, like we said. Mismatch is a huge error, but those are statistical errors that can't be contributed. And there's other errors that we're going to be looking at. So, you know, and we got to make some kind of judgment on these. And naturally, as metrologists, we want to be able to look at all these measurements, you know, and some of these measurements where we don't have enough information, you might want to run a test. Let's say, for temperature, you know, you might want to take your test and run it through a temperature, and that way you get a better value, a better understanding of exactly what is it that you're looking at, you know, and its effects with a change in temperature. So there's ways that we can do that, and ways that we can adjust and make measurements a little better in our process. So once we look at all these type of measurements, and we separate them, and we know what kind of goes what. You know, now it's time to really combine these. We need to get the errors into a standard deviation. You know, for us to be able to look at various vectors within the data. So we need to calculate and estimate the individual A and B uncertainty contributions, and those are with the formula that you see there. That is the formula that we would use in order to be able to combine those errors. The combination of the uncertainty is a basic estimate, and it represents one standard deviation. So, and we'll look at that one standard deviation a little bit more. And then basically what we're going to do is that we're going to use the root sum square of the errors, and we're going to look at that, and then you know, we'll assume that the contributions are independent. If they're not independent, then we may need to do a little bit more. And I'll have an example later on of what is a non-independent, you know, kind of a measurement that we would want to go through that. And naturally, once that we have all this, you know, the corrections between the contributions require additional considerations. That's exactly what I just said. You know, for those that are not independent from, we need to look at them. We may need to do a little bit more math on the side and get those up to where we need to. So we'll estimate that error, and we'll just kind of move that right along the source. So what we'll do is we'll basically look at the concept of the standard deviation. So, you know, the basic standard is, or the basic concept is that the equivalency is one standard deviation. That means, you know, that 68% of a value will be in that. In this, you know, then we can look at 2 sigma and 3 sigma and look at and different factors. But typically what we're going to do is that we're going to correlate everything. We're going to get it down to one standard deviation. Then we're going to combine those, and then we need to do get standard uncertainty, and then we need to upscale that to move it into wherever it is that we need to. So in our case, we typically in calibration, we talk about 95%. So if you look over to the right on the table, 95% is really 1.960, which is the K factor factor, we typically always round that up to 2, and we use that 95 as a K equals 2. So that's kind of where it really comes from, and that's how we're, we just move it along the table. Let's see. So once we get it into that one standard deviation, then we can do what we call a scale up. We'll move that up. We'll get to a coverage factor, the one that we want to represent. Like I said, it's typically 2, and which indicates that it's 95%. If you actually really looked at what 2 is, the K equals 2 is actually a 95.45, but in the industry, it's very very well understood and common that we use 95, and we use the 1.96, and we'll leave it at 2. So we just round it up. It gives us the values that we need. So value that we'll put on the certificate. So when we look at the type of contribution statistical characteristics of these, the probability of distribution comes in many forms. So here I'm representing several of them. We have the normal or Gaussian. We have the rectangular or uniform. We have U-shaped, binomial, and triangle. So we look at these. Each one of these have a divisor which will get us back into that one standard deviation, and then what we look at. So if we look at the have that at the far left one shows a normal or a Gaussian distribution. Typically what we use this is on typical associated where the errors are random. We just don't know where it's going to go. So it's a manual process, so we're just going to take a whole bunch of data and we'll see what it looks like. On the center we have what we call the rectangular or uniform, and this particular case is we typically use this type of distribution, probability distribution, for that are a specification, a manufacturer specification. They gave you a specification. We know that it's going to be between a value of X and Y, so or plus or minus whatever the error is. So we know where it's going to go. We just don't know exactly where it's going to lie. So we just have a area where we know that value is going to lie. Then we have something that we have a U-shape. I'm not getting into the U-shape right now because we're going to do that later into when we get into the mismatch. We'll look at those and we'll talk about that. And then we have, or binomial, then we have what is known as the rectangle, and that's pretty well when we know that where it's going to lie. So and there's other influencing factors, but and we'll get to that also. So what's important really here is to be able to characterize or put your correct distribution associated with what you're trying to do. So if we're doing a random process, you would know that it is a normal distribution, Gaussian type. If we're looking at a manufacturer specification, then it's a rectangle, and so on and so on. So it's important for us to be able to identify exactly where it is, and remember that we're going to use a divisor to get us right into that one standard deviation, because we're going to combine them as we showed earlier on one of the presentation, on one of the slides. Then something that we need to do is we want to look at the degrees of freedom. And basically what this is telling us is how big is the sample? The value and the amount of the information that was deployed with the estimate. What did we do? So usually that sample is what we call an N-1, because it's a sample. It's not the total population, and we'll look at that a little bit later. And this is typically considered in the 8-type uncertainty. So we'll look. Another thing that you can often say it's the variance. It's the variance of all the data that we're taking. So we know. So we'll calculate the variance. We'll calculate the mean. We'll do an analysis basically of all the data that we have taken. Obviously, also consider the infinite, and this would be something such as a manufacturer spec. And that's because the specification tells us it's plus or minus this, and we can just kind of move that. And the sensitivity coefficient is how influential all the data was. You know, the measurement response by dividing by the corresponding change. The change is often a value of 1, and so is the sensitivity of how well the instruments or the data will correlate with this. This is what's called the center limit theorem. As you can see, and hopefully you guys can see it well, you can see that whether we have a distribution that is gaseous, or it is rectangular in nature, or it is a triangle, they all fall pretty much. The distributions fall within the Gauss distribution. So it's pretty well for us to say that when we get it to one standard deviation, we know that, you know, hey, we are looking uniformly at all of them in the same aspect. The central limit theorem it's a formula. You can look it up. You know, you can go and evaluate it. Basically, it just kind of gives us the shape of what that normal distribution should look like. So it allows us to say, yes, we can combine it. We can combine a rectangular with a you know, just because we can see it. We can see where it's going to lie within the combining uncertainty distribution. So it kind of resizes that, yes, that what we're doing, the process that we're doing, and the different types of distributions that we have, we can combine them, and we can combine them a lot better when we get them to that one standard deviation. The thing that we really need to look is the factor and how we're going to adjust that. And you know, this wasn't very big many years ago, and you know, as time has evolved in metrology, it's gotten more and more of an impact. So, and it is quite impactful now. So typically, it only applies to B-type distributions, and look at it so we can get it all to that factor of you know, of K equals 2. So basically what we look at is that we have a degree of freedom on the side of the chart, and then we have the what's pitch factor on the other side. So in order for us to be able to utilize the table, what we need to do is use the Welch-Statter formula, and then this will give us an overall effective combination of the degrees, so we know how well we're doing. So, and it really involves, it may look complicated, but you know, if you put that in Excel, it's quite easy to utilize. You just enter the data, and you know, it'll populate everything else. But basically, what it's going to do is going to take the sensitivity coefficient, is take you know, the combined standard uncertainties, is going to look at the individual standard uncertainties, and it's going to look at the degrees of freedom, and it's going to use that. It's going to multiply it up, you know, where you see in the formula, and then it's going to give us an effective value. We tap value, and now that we have a number, we try to approach as close as possible to what's called, you know, K equals 2. So in this particular case, we always want 95 because that's the reporting factor. So if you go to 95 and you go all the way down to infinite, you see that it's actually 1.96, 96, which, you know, what we were talking about a little bit earlier, but we want 2. So you can look and see that as you go down the number of degrees of freedom, we want to approach a value somewhere within 10 to 20, or you know, even 50. But that number right there, the 2.09, will get us right pretty much where we want. It allows us to make sure that mathematically we can move that factor right into what we're trying to do, and adjust and make any adjustments necessary, you know, to our calculation, so we can make sure that that we report a good error. So if you looked at 95.4, you can see that the infinite number would be 2. It's going back to the table that we talked about a little bit earlier. Reach an infinite number is very difficult. We'd have to take lots of data over and over and over, an infinite number. So this is just to just kind of look at certain data points and measure them. But you have to remember that these data point is n-1 because we're using the standard deviation, and we'll get into the formula here in a little bit, and then we'll look at. So if you took 10 readings, you would actually be looking at the degrees of freedom of 9 because it's n-1. So that would be a 2.3. So we would have to look somewhere like 20, 21, and that way it'll get us closer to that k equals 2. Really need to worry about, and it's quite critical in all our measurements, is pretty much the being able to talk in the same unit, especially in RF and microwave. We talk dB, we talk power, we talk voltage, we talk all these type of different measurements. So we have to make sure that we convert all logarithmic measurements into a linear measurement, into a linear quantity. We want to be able to do that. Errors that are very insignificant will catch up with us later on if we don't do that. So when we talk about an absolute value, we want to make sure that everything that we're doing is an absolute value. So we want to combine everything to the same base unit. Extremely important that you always combine to the same base unit. So if you're talking to relative, you got to make sure that everything is in relative. So if you're talking to absolute, whether it's watt, milliwatts, or whatever, you are in, all your values are in that. And what we'll do is we've got to make sure, especially when you're adding or subtracting like dBs, that's a asymmetric unit. So basically what that tells you is that if I had a change of 0.1 on the table on the right, if I had a change of 0.1 dB, right, a positive, you see that is a 2.3% error. But if I have that same 0.1 minus, that's a change of 1.28. So there's already a difference, and these can accumulate throughout the formula. So it might, you might say, well, it's not big enough for me to correct. You should always correct. You could say, okay, the plus 2.3 is the biggest percent of error, so I'm just going to utilize that. Also acceptable, but you have to make sure that it is, that is the worst case, and if that is what you're correcting. So you can see like 1 dB. 1 dB is about 20%, and you can significantly see that 1 dB is plus 25, 0.9%, or minus, if I subtract that from my value, it's minus 20.5. So you can see that there's a dramatical change in that. So being able to stay within the same base unit is, and correcting could correct in your measurement. So you have to make sure that you're doing that. So what we need to remember is that power and voltage are related. One's the square of the other. So on some places you're going to do a log 10 and others in log 20. So you have to be able to make sure that you're at that. If you're very aware that you talk in the same language. So if we're talking percent of power, or we're talking in watts, or we're talking in dB, or we're talking in milliwatts, whatever the case may be. So you have to be careful all around, especially with that isometric errors. Those are the ones that are going to get you every single time on your sheet, on your uncertainty budget. So use extreme caution when we're calculations here. Go to the next slide. So here's where we're looking at a type A question. So, like we were talking earlier, this is typically where we'll look at short-term variances. We'll look at some noise. We'll look at different types of measurements and the impact of those. So we might want to take several measurements, typically 5 to 10 measurements somewhere in there, and that way you have a good example of exactly what's happening within your measurement. And in this particular case, when we would look at this, we would look at a distribution that is a Gaussian distribution or a normal distribution. That means that we know it's a random and it's going to lie somewhere between one factor and the other, or, minus. So we have to make sure that we understand that, and we also have to make sure that we understand which sample we want to use. Do we want to use a sample deviation or do we want to use a standard deviation? Well, you always use the sample deviation. The population, if you were open up Excel and you try to convert something in Excel and you ask for the standard, you'll notice that there's a couple of different formulas for the standard deviation. One would be a sample and the other one would be a population. So extremely critical, important for you to understand which one you're going to use. So since we're going to use the sample because we're not going to take all the readings, we don't know everything about it. We make a lot of assumptions, and we want to be able to look at that data, correlate that data quite well. We're going to use the N-1. And it's the one that is typically used for all calibration, for all testing, not necessarily calibration, just testing in general. So we'll look at that. This is where we're going to get it to a one standard deviation, and let's see, what else can I tell you about this? The slide here. We're going to assume that it is normal, the normal Gaussian distribution, and that we have sufficient samples. The sufficient sample is going to be, the 5 to 10 samples. We want to be able to look at those, and then we will be able to repeat that process. Want to look at a couple of times, what can we do to get that into the best measurement. Now assume it, but with 1 or 2 samples, take several samples, a good amount. Remember that this is going to go into your degrees of freedom, so you're going to be able to look at this and make a quantitative value of your measurement. Another influence in your measurement, and that's the connector repeatability. Connector repeatability is probably, along with mismatch, should probably be your biggest contributor to all of that. How many times have you removed a cable from measurement, you reconnect it, and you get a different measurement, and you do this a couple of times and you get that? Well, the same thing with connectors and RF. Sometimes you can wiggle a power meter and you're going to slightly get a different measurement. So how do you know that you're at the same location, or at the same tightness and everything else every single time? So this is what we consider a type A uncertainty. Being a type A uncertainty, we can sit through statistically because we adjust for it. We make those repeatable measurements in that connector. A good rule of thumb is 3 to 5, minimum 3, ideally 5, and we want to be able to rotate the connector. So it's not just a matter of connecting and disconnecting and making the measurement, but try to rotate the connector, because you've got to look at the quality of a connector. If I always use it in the same location, same place, I'm going to do that, but you're not. Your connector will vary the reading. So critical would be is do you gauge your center pin on your N-type connectors? If you don't get them, then they're going to be different every time you put them on, because you don't know exactly what it is. Is it to manufacturer specs? Which brings into the example that they have here. If if your pin and the depth of the pin and everything associated is to manufacturer specs, then you can take this IMAT and specification right here, and you can say that this is the repeatability of that cable or that connector or whatever it is that we're measuring, because it is mathematically calculated. So you have a very good idea that the measurement is going to be repeatability on the insertion loss because it is mathematically, or you're checking it. So you're constantly checking your connectors, which brings up that connector care. Connector care is huge in this because if you have good connector care, it's clean. You've measured the depth. You've inspected it. You don't blend it. You don't. You just take good care of it. You'll be able to make a good assumption that the connector is good and is provided. There's a paper that is written, and you can look at it right here. Everybody will get a copy of this presentation, and it's the IMEC Guide to Using Precision Coaxial Connectors in Measurements, and show you that the repeatability of those of connectors. So, and like in this example, is that it has it for different frequencies, because if you're following the proper connector care, then you can make this assumption. So it's not something that you're going to have to test every single time. Otherwise, you're going to have to test it every time, and that'll go by rotating the connector, throughout its 360 degrees, trying it in different positions, moving the cables and so on and so on. So extremely important. There's a whole bunch of important information at the end of guides and references where you can go and look at this, and you'll see that the impact just of what the cables will have, and which ultimately affect your mismatch and reflection coefficient and everything else. The thing that you want to look at is definitely in RF and microwave is going to be the mismatch. And in mismatch, we typically use what's called a U-shape distribution, and we're going to talk about that a little in just a bit. So we'll look at the mismatch. Typically, when you look at mismatch, you look at worst case in magnitude, and we typically don't have phase information typically. For example, as you show there, is that the VSWR, or the reflection coefficient. And to make a note is that the divisor for a U-shape distribution will be 2, so square root of 2. So that's the number that you'll use in order to get that to a standard deviation. And impacts that will happen into your measurement is that if we look at that transmission line, signal through that transmission line, we're going to get sources of error or reflection, or that reflection coefficient, and we'll get some that are caused by, let's say, the generator, and the other one may be caused by the I just noticed that in this presentation there's a formula that's missing, and it's the gamma on the very bottom, the gamma information or gamma formula. I'll make sure that when the presentation goes out, that formula is on there. And well, when we have gamma, and the reason I noticed that is because when we have gamma, now we have a lot more information. And when we talk about gamma, we typically talk about a power meter measurement. So when we're talking about that, we have a lot more information than we do when we just have reflection or magnitude. So the calculations would be different. We'll have to take those off to the side and do some calculations in order to try to bring those back, convert those into a standard deviation, and then bring them back into our budget table. So these just need to remember that as you're processing this, you'll have magnitude and phase. And in other words, what ends up happening is it purely resistive or not. So you need to look at that and make an assessment of the worst case. So what we look at in this is in this U shape is that we look at the worst case limit of value, because all we have is the data. So when we look at that, we're really looking at this as in a polar diagram. So if we take that U shape and we look at we're going to take the worst case. So the contributions are going to be maximum. So because we don't know anything else. So we have to make, a good judgment to say, okay, this could be the worst SWR that I'm going to have in this measurement, and that's the one that we have to utilize because we have no other data. If we had the gamma, the magnitude in the phase, then we could make other calculations, but typically we don't. We don't have unless you're using bridge, unless you're using a vector network analyzer where we can utilize all this information, then you could bring that up. Other than that, this is the best that you're going to get, and so you'll have to make a contribution based on those measurements. And naturally, this is on the form there. There's ways to do it in voltage, and there's ways to do it. And so you can go back and forth, return lost or reflection coefficient. So different points will get you into different types of parameters. So we're going to talk a little bit about that mismatch error. So we know that that the mismatch, if the mismatch is known, then we have an SWR value. The uncertainty of the measurement value should indicate when calculating the mismatch uncertainty contribution. So basically, what this is telling you is that if we have both the source error and the load area, the load error, what we're going to do is we're going to combine those and come up with an uncertainty value that we're going to bring back to the previous formula and apply that into our budget uncertainty table. So this is basically taking all the other derivatives that we don't have that we're going to add and transform over. So it's just be able to see that these are all the different factors that can play into measurement. So if we have magnitude in phase, like we were talking about a little bit earlier, that would give you that gamma. Then we would need to do a little more outside calculations and bring those back in. But typically, what we're going to do is that we're going to be looking at the match parameters and use those, and then be able to take those measurements and bring them back into the table and use them at a one standard deviation, and then upscale them from that point up, so we can make those values. So we make those calculations, those adjustments to that. So the other thing that we need to learn to handle is building the manufacturer specifications. So typically, when you see a manufacturer specification, they just tell you it's plus or minus X and Y, but they don't give you much more data other than what we have. So when we take that data, we actually use the rectangular or uniform, or rectangular probability distribution, because that's all the data that we have. If we had something else, then we could use another type of distribution, but that's all we have. So you take sufficient measurements. You come out with your plus or minus specification, and then it's you divide by 3, the cube of 3. So that'll get you right back into that one standard deviation. This very typically associated. All we have is the manufacturer spec. Now, in some occasions, what you'll see is that, or Fluke, one of the things that Fluke does is that we'll give you a specification that'll say 95 and 99. So that means that we're giving you already more data. So by being able to give you a 99, now we change our type of distribution because we know that the value is going to lie somewhere to that mean. So we are able to look at the normal distribution versus a rectangular distribution. And that's simply because we at Fluke, we apply the 95 to calibration tables, or not calibration tables, I'm sorry, to calibration certificates. Yet for manufacturer specifications, we have better confidence that we're at a 99, so we can give you another assessment. So it just gives you another factor to be able to do that. And the other reason that we give you a 95 is because most people may not know how to convert from one to another, move it from a 95 to a 99 or vice versa. So we just go ahead and do that. So in this particular case, the dividing factor or divisor would be 2.58. So it would be especially moving you right back to that one standard deviation. Doing in time here. Here's the next thing that we have to look at. We have to look at the sensitivity coefficient, and that's the relationship of influence of the quantities of the uncertainty contributions and the overall measurement result of the memorandum. So this is where we're really going to look at how does one affect the other, the sensitivity coefficient. So in the example that we have here, the effective, what we need to do is look at as the effective and derivative, the effective partial derivative of the relationship between the influence and the quality of the memorandum, and that's what we see in example 1. So as we're going through it, you can see that going power is relative to voltage square, so we have a sensitivity coefficient of 2, but if we were in voltage, it would be 0.05. So there's a sensitivity factor that needs to be applied depending on what you're doing. And the other example that Paul had in this presentation, he shows that although we're calibrating the oscilloscope and we're looking at the bandwidth oscilloscope, we see that there's not a good roll-off. So we need to make a good measurement across that roll-off to come out with a good number, because it's not gonna, a best fit number kind of. So it's not exactly the 707 and the 3 dB cutoff. So we need to look at that slope and able to normalize that slope and put that into the uncertainty, because that would give us a better measurement. I mean, we can just say, okay, at 3 dB, this is the number, but we want to actually look at it better, because there is a slope and there is measurements throughout the slope. So we want to use that technique. This same technique that we can use when we're calibrating a spectrum analyzer. Now moving into a spectrum analyzer and looking at that. As that we would do that, we would be looking at resolution bandwidth. We would be looking at shape factoring, testing, where we have to do the 3 dB or the 60 dB bandwidth point. So, just slightly different where we're going to do that. So it's a little bit more critical than just saying, hey, let's take the 3 dB bandwidth and measure it, and we'll apply that to the table and we're good to go. So you want to be able to dig a little deeper and, come up with the slope curve, and then apply that into your budget uncertainty table. Now you have a better measurement. And that's the part of that metrologist that should come out in you and say, okay, what are all my variables that I can really make or influences that I'm having in this measurement? So that's just a good example of that. And that's because in that particular case, in example 2, it's not perfect. It's not a perfect measurement. So we've got to be able to make that judgment and go and make different points, take different calculations, and be able to say, okay, this is going to be my worst, this is going to be my best, or what's the best fit, this is the best that I can do. So here what we do is, what we have is, basically what you're seeing is, although this is a scope, there's a combination of everything that we just talked about. So you can see that this is probably part of the of an Excel sheet that somebody made. This is their table where they came across. So these are all the factors that they calculated within their measurement. As you can see, this was the line for up to 6.4 gig. They calibrated the peak-to-peak voltage, but using a power meter. So there's an adjustment that needs to be made there. The illustration right there is the spreadsheet that I was just talking about, and the relationship of voltage and power. So if we look on the left-hand side, we can see towards the bottom all the frequency ranges that they checked. And then as you notice up on the top, you'll see that there's different factors that they had. They had the power sensitivity, the power sensor and calibration factors for both the reference sensor, right, and the test frequency. So it was, hey, on one of them we got a test report, and the other one we don't have anything. We're just taking a measurement. So we've got to be able to apply both. So then if you move across, you'll see that there is a power sensor stability. That's part of a measurement. So we want to be able to look at that. Then we have to also look, okay, what's the other impact that we have in this voltage? Is that, hey, we have a power sensor linearity, which can definitely affect our measurement. So we've got to be able to look at that. Now here they combined the resolution in noise, because one may not have, the combination of both, it might be sufficient in order to come up with the value, because if resolution is small, we're not really going to see much of the noise. So have what is called the mismatch of the connectors. So you can see in the picture up on the top right that there is a BNC, and then there's a N-type connector connected to the power sensor. So there is a mismatch in there, so we need to account for that type of measurement. Now there's also that connector repeatability, and as you can see, going right across, we can see the different type of measurements along with the affected degrees of freedom, and then we can look at the expanded uncertainty at 96. But if we look at those, you can see that they have the distribution type, they have the divisor, right? They have the sensitivity coefficient. Have the degrees of freedom in the quantity of the measurement, or the base unit that we're really looking at. That base unit being power, or in this example, it would be power in peak to peak. So as we look across, you can see that the distribution, we use two normal ones, and then we went to a rectangle distribution, right? We have a U-shaped distribution, and you can see that the divisor changes because for every different type of distribution, we have a different divisor. So you can see these are already been calculated out, whether it was the square root of 2 or the square or the cube root, or the square root of 3, or it was a 2.58, just depending on whatever it was. Now that helped us develop a sensitivity coefficient. We see that where we were making Cal factors, the sensitivity coefficients were 0.5. Where we're making power, it was 0.5 as illustrated earlier in one of the slides. But yet, you notice that they have a peak-to-peak measurement here also. So that changed the sensitivity to 1. So don't know why they didn't do the conversion factor automatically, but that's what it is. So then they go back to power, and you can see that they repeatedly just kind of change the factor depending on the type of measurement. And then the degrees of freedom. A good example of being able to handle degrees of freedom. When we're making this measurement, the measurement is infinite because it's a Cal factor. There's really no calculations. But in order to be able to handle this through, say, Excel, because in Excel you can't have an infinite number, 500 is good enough to get us right to the value we need to be. From that point on, it really would not affect our measurement. And if you remember the table earlier, you get to a point where the values are just really not going to change. So if we move across and we look at the power meter and noise, you see that the degrees of freedoms, though we took 10 readings, it was N-1. So there's 9 readings. So that's how we'll adjust to be able to get us to the K equals 2 based on 9 readings. This thing happens to the connector because, it's the same connector that we're using to make the reading. So there was 10 readings, period. So for the connector degrees of freedom, it'll take us there also. And the quantity, we talked about that a little bit ago. We got a correction factor, we have a power, and we have a peak to peak. So we make that correlation and we adjust accordingly. And you can see below that as we're going down with frequency, our values are changing naturally, which changes the estimated uncertainty also at each individual point, not overall, because that when we're reporting that K equals 2, but there is individual parameter measurements throughout the entire sheet. So type A, repeatability, we at that. That's the 10 measurements that we talked about. We're reporting 9 because of the N of -1. We talked about a little bit about making the infinite number of readings. It'll get to the point where it's not really impactful. You've got to make that determination where that is, and then looking at it and coming up with your budget. Thing that you may want to look at is automated processes, where processes can be automated and help you do this a lot faster. One of those methods naturally for us is Metcal, where we do some of these readings and we report, and it's got a little more flexibility. And you do have to program it. You do have to get it to take the values that you want. If you look at it, this is basically the data that we get out specifically out of Metcal. So in this particular case, where they built this PowerPoint show, and that's because it was just kind of simple, and and the data is pretty straightforward, but the data would be the same regardless of what you're doing. So we would look at this. In this particular case, you can see that they made the measurement details, and then the repeatability. Now you see that the degree of freedoms in the repeatability is 4 because it's N-1, and then we can look at the standard deviation of the. We can look at the standard uncertainty. We can look at the sensitivity coefficient, right? And then we can get into the calibrator, details of what we did, details such as, hey, we're testing the 10 volt, what is the system accuracy, what is the confidence level in that particular case, 1, as you can see, sigma 1, and sensitivity coefficient, and look at the degrees of freedom in the calibrator. It's to 1 2 plus 200, and that's because the reading is infinite. So we'll get to a point to where we're just going to put a value that's not really going to affect our measurements. So let's see, and then the resolution of the uncertainty, and then at the end it gives us the extended uncertainty, and it gives us all the information. So going through a automated procedure is a very good way of looking and trying to sort this. Naturally, as the metrologist, you always have to be able to tell the auditor how you came up with those results. So if you're using an automated system, you'd be able to go to the auditor and tell them exactly how all this was derived and where you can find it. So very important for you to that. Also is to be able to understand exactly, everything that is a contributor to your measurement. Define your specifications, define your test, and define all the possible errors, and document it. Document everything. Exactly where you're at and why you did that. It's back up to be able to prove to an auditor exactly what is it that you want. And being able to understand the measurement process, exactly what you want. Keep a record. Be able to make very intelligent decisions on why you're testing that particular point. Why did you select that, or why are you selecting these points, and so on. All these can be found in these references. They already gave me a 3-minute warning. So all these can be found in these. Actually, I think on the next slide you'll find where a little bit more detail on every one of them. If there's anything specifically that you want to know, just go ahead and shoot me an email. Everybody will get a copy of my email, and we'll be more than happy to answer it. If not, if you want to go and look for the reference yourself, here's all the references that we have. Extremely important, and most people are not aware, is that I'm at the Guide to Precision Coax nectars in measurements. Extremely important. Please take the time to go and read it. This is all great information, and let me see. And Bruce, you want to take us through these?
No, go right ahead, Bill.
Okay, thank you, Bruce. So we do have other WebExes coming up. We just had some for RF and microwave fundamentals. Went through how to identify some and avoid some of the RF errors. We did this budget uncertainty. We have a couple more coming in September, and we do also have one in November. So please feel free to go to any one of these that is already online. You can download it, listen to it, share it with your partners, forward the link, and that way it could be a topic of discussion. If you need to bring us in, we'll be more than happy to do that. There are a couple of training courses that are available, whether it's metrology training, whether it's classroom, whether it's a self-paced, online training. We can do all that for you. We'll be more than happy to do that. There should be a Fluke representative in every one of your locations or countries. If you're not sure who they are, please don't hesitate to write us, and we will make sure that you get all the technical help that we can provide. And with that, anything else, Bruce?
No, no, Bill, thank you. Very, very informative session. Very well attended. I apologize to our audience that we won't find to run along. We won't find to go through a online Q&A. But as Bill mentioned, please feel free to email Bill the questions you may have about this session. And we'll get questions at our celebration. We'd be happy to again.
So I said I ran over the 45 minutes allowed. So if I can get a copy of all the Q&As, I'll go ahead and respond to those as quickly as I can. You get this within 24, 48 hours, typically. Bruce, is that correct?
That's right. And those who have attended will receive a link to the recording of this session. And we thank you very much for attending. And Bill, thank you very much for your presentation. So with that, I'll go ahead and any closing words, Bill?
Thank you very much, and please don't hesitate to give us a call or shoot us an email.
All right. Thank you very much for attending.
Thank you.